All right, hello chemistry students. So I just wanted to post one more video to kind of show you and wrap up where we are, kind of to summarize the same instruction that we did last time we met in class in terms of where we stand in our ability to convert to and from moles. So far in the videos, our conversion chart has looked something like this, where we're able to convert between molecules and moles using Avogadro's number as a conversion factor, using that 1 mole is equal to 6.02 times 10 to the 23rd molecules. 1 mole of any substance is equal to 6.02 times 10 to the 23rd molecules. And then we've been able to convert between moles and grams using the periodic table and using the conversion factor that 1 mole of any substance is equal to the atomic mass of that substance in grams. So for example, oxygen on the periodic table is 16.00 AMU. So 1 mole of oxygen atoms equals 16 grams. So if we have 1 mole of oxygen gas with the chemical formula O2, since that contains 2 oxygen atoms, that would have a mass of 32 grams. So we're pretty good at doing that at this point. So what we're going to add is 2 new ways to convert into and out of moles. Specifically, we're going to be using volumes of a gas at standard temperature and pressure, and we're going to be using solution concentrations, also known as molarity. So the reason we need to do this is because for an aqueous solution, we don't really have a good way to weigh that aqueous solution. If we have a bottle of something that's dissolved in water, most of the weight of that substance is water, so we can't directly correlate the mass of a liquid or an aqueous solution with the amount of moles of the substance that it contains. So that's the reason we need molarity. And for a similar reason, we need a conversion for volumes of gas because it's just impractical to take a gas and weigh it on a balance under most normal conditions. So we have 2 new conversion factors, and I'll start with the easier one first. Our conversion factor between moles and volume of gas is that 1 mole of any gas at STP, which stands for standard temperature and pressure, is equal to 22.4 liters of gas. So if you have a gas at STP, and STP is standard temperature and pressure, then 1 mole of that gas will take up 22.4 liters of space. That will be the same no matter what gas you're using. So if you're talking about oxygen, or methane, or nitrogen gas, or hydrogen gas, it doesn't matter what type of gas you're talking about. For any gas, 1 mole of that gas at standard temperature and pressure will take up 22.4 liters of space. So we can use this as a conversion factor to tell us how many moles of a certain gas that we have. So for the last conversion that we can do, we need to be able to convert between the number of moles of substance and the concentration or molarity of an aqueous solution. Now, molarity is a new term, and as I said, you can think of molarity as being how concentrated an aqueous solution is. And molarity is symbolized with this capital letter M. So the equation for molarity is that the molarity of an aqueous solution is equal to the number of moles of solute divided by the number of liters of solution. Again, the solute would be what you would dissolve, and the solution would be the end result. So for example, if you were making Kool-Aid, the solute would be the Kool-Aid powder, and the solution would be the end Kool-Aid that you get to drink. So again, molarity is equal to moles of solute divided by liters of solution. We can summarize that with molarity equals moles per liter. This is an equation that you'll need to memorize. It will not be on your exam. So we also need to be able to use this equation in a variety of ways. we need to be able to take any of these three variables, molarity, number of moles of solute, and number of liters of solution, and given any two of these variables, we need to be able to solve for the third one. So I've listed over here the various ways that this algebraic equation solves itself. So the first one is solving for molarity. So the molarity of a substance, as we said, is equal to moles of solute divided by liters of solution. If we wanted to solve for moles of solute, what we would do is we would multiply both sides of the equation by L. And that would give us molarity times liters of solution is equal to moles. And then last of all, if we want to solve for liters of solution, we could take this equation, divide both sides by molarity, and we would end up with liters of solution is equal to moles divided by the molarity of the solution. So you need to be able to use all three of these. You need to be able to understand how to get from one equation to the other using simple algebra. If you struggle using simple algebra, then you could simply memorize these three equations and use them in whatever case that you need to in order to solve whatever problem you're given. So let's just do some quick example problems to show how this works. So the first problem is how many moles are in 11.2 liters of carbon dioxide at STP. So the way we would set this up is we write what we know, as I showed you in the railroad diagram video. So we have 11.2 liters of carbon dioxide, and we know from our conversion chart that 1 mole of any gas at STP is equal to 22.4 liters of gas. So we're going to convert from liters of carbon dioxide into moles of carbon dioxide, with the conversion that 1 mole of carbon dioxide at STP is equal to 22.4 liters. So if we take 11.2 and we divide by 22.4, since it's on the bottom of our railroad diagram, that gives us 0.5 moles of carbon dioxide. And this is a pretty simple process. This conversion between moles and liters of gas will always be the same, and it will work for any gas. In the same way that our conversion between moles and molecules is always going to be 1 mole of anything equals 6.02 times 10 to the 23rd times 10 to the 23rd molecule. Sorry for the voice. Okay, so let's look at another problem. What is the volume of 2 moles of methane gas at STP? Okay, so we see volume of gas at STP. We know that our answer is going to be liters of gas, and we know we're again going to use this simple conversion, that 1 mole of gas equals 22.4 liters. So we'll set up a railroad diagram. We start with what we know. We have 2 moles of methane, and we're going to convert from moles of methane to liters of methane at STP, with the conversion that 1 mole is equal to 22.4 liters. So in this case, we would take our 2 moles, we'd multiply by 22.4 since 22.4 is on the top, and we'd end up with 44.8 liters of CH4. Again, a very simple conversion. So these types of problems would allow you to get into and out of moles for your stoichiometry problems in order to follow the steps that we covered in the other videos. In the same way, let's look at a problem like this. How many moles of ammonium hydroxide are there in 3 liters of a 6.0 molar solution of NH4OH, of ammonium hydroxide? So the way this works is we know our molarity equation is molarity equals moles of ammonium hydroxide per liter, moles of solute per liter of solution. We can rearrange that to solve for moles by multiplying both sides by L. Liters would then cancel on this side, and we would end up with the equation molarity times liters equals moles. We're given the molarity and we're given the liters, So all we need to do is then plug them into this equation and solve. So 6.0 molar times 3.0 liters would be equal to the number of moles of NH4OH. That gives us a total, 3 times 6, of 18 moles of NH4OH are present in 3 liters of a 6 molar solution. So again, for the molarity problems, all you need to do is to be able to use this one equation and rearrange it in order to solve for any of these 3 variables. In looking at this problem, we would know to use the molarity equation because we're given a volume and we're given a molarity. So we're given 2 pieces of this puzzle and we need to solve for the 3rd one. And that is how we will know to use the molarity equation, and then all we need to do is apply it. So I hope that makes sense. Again, just as a recap, if you know and understand this figure and can convert into and out of moles in any way, that will benefit you for the exam. You should be able to start at any point in this graph and to move to any other point given an amount of a substance. So if you're given the volume of a gas at STP and they ask for how much that is in grams, well, you would convert to moles and then you would convert to grams. If you're given grams of a substance and you want to know how many molecules that is, you should be able to convert from grams to moles and then from moles to molecules. So I hope that all makes sense. Let me know in the comments if you need clarification on anything, and I will post another video later this week. Thank you very much.